Okay, so here's our second equilibrium problem. This one's going to be a little more involved because we have two different types of forces. We have horizontal forces represented here and here, and we have vertical forces represented here, here, and the weight of the board there. So we have three things that we have to add together. So the first thing we're going to do is we're going to split this diagram apart so that we can go to just looking at the forces. So I've drawn the forces and I've labeled them. You can see I have N1, which is a normal force on the ground, N2, which is the force of the wall back up against the beam. We have a frictional force down here, and we have two weights. One is the weight of the block, and the other one is the weight of the ladder. So we're going to have to add these together. So before we do that, we're going to separate these out so that we can see the torques. So the next step is we'll redraw one of the weights right here and the N2 force from up there. So if you see that, what we're looking for is this perpendicular line. This is what's going to cause the torque. So if this is W, either 1 or 2, then because this is a 60, 30, 90 degree triangle, this has to be 30 degrees, which makes that 60 degrees. So this side that's perpendicular is going to be W cosine of 60. And that's going to be important when we do our sum of our torques. Likewise, when we go up here, from alternate inferior angles, this is 60. That makes this a 30 degree angle. And then it'll be N cosine of 30 for the torque. So we're going to use both of these values when we do our torques. So let's first sum each of our values. So we got a sum of our X forces, and we have two of those. They are N2 and F, and that has to equal 0. We have a sum of our Y forces, which will equal N1 minus W1 minus W2 has to equal 0. And then finally we have our sum of our torques. And this is all dependent on where we put our rotation point. And if you remember from class, we can put it anywhere we'd like. So we're going to choose right here because that eliminates two forces from our torques. So our first one going up from there is going to be W1. So we'll go down to here. So it'll be W1 cosine of 60 times the displacement. So W1 cosine of 60 times L divided by 2 because we're halfway up the board. This will be a negative because it will cause the object to rotate in a clockwise direction. And then we'll do the same thing for W2. It'll be exactly the same except for it'll be cosine of 60 times 2/3 L. And then we have to add to that N cosine of 30 times L has to equal 0. So we're looking at this equation right here. This is the one that we're going to go because we can put in numbers for all of these values except for N2. So first thing we can do is divide all the L's out. And I'll simplify things quite a bit. So N1 is the weight of the beam. So we do 50 times cosine of 60 divided by 2. Remember that's negative. Minus 60 cosine of 60 divided by 3, and all of this has got to be multiplied by 2 plus n cosine of 30. We're running out of room here, and that all has to equal 0. So we solve that for n. So n2, we do all this mathematically in our calculator and in our heads, and n2 will come out to be 37.6 pounds. So that's one of our answers. Now, if we look at our second equation, our fx equations, fx, we can see that we have n1 minus 50 minus 60 equals 0. So n1 has to equal 110. Where am I? 110. So there's our second answer. And then finally, our third answer, we go back to the fx equation. And we have n2 minus f equals 0. So we already know that n2 is 37, so f has to equal 37.6 pounds as well. So there are our three answers. And you can see this is a little bit more complicated, but by choosing the rotation place, it does come out fairly easily.